Okay, so this is chapter 7, section 8, improper integrals. So in this section, we extend our concept of a definite integral to the case where the interval is infinite, or also the case where f, the function f, has an infinite discontinuity in the domain from a to b. In either case, the integral is called an improper integral. So the first case we're going to look at is cases where we have infinite intervals. So type 1, infinite intervals. So consider the infinite region S that lies under the curvature of y equals to 1 over x squared above the x-axis and to the right of the line x equals to 1. Okay, so here's a nice little image. Right, so here we have the function 1 over x squared. Right, notice that it's always positive. And we want the area trapped between the x-axis and the function 1 over x squared. So that would be this little blue region to the right of the value, x equals to 1. And so this would be this little region here. And this goes on forever, right? Forever and ever and ever. So we're going to know what is the value of that. So the way we're going to do that is to set up the integral that goes from 1 to infinity of 1 over x squared dx. And then in order to be able to solve that, we're going to apply limits. So we want to let t go, we want to replace it with the integral 1 over the integral as that ranges from 1 to infinity of 1 over x dx, and we want to replace that with this, the integral from 1 to t of 1 over x dx, and then apply a limit as t goes to infinity, right? And so as long as we're able to figure out what this integral is, with t being kind of a stopover, like a placeholder for some constant that's to the right of 1, so if we can figure out the answer for some specific value t, and then let t go out to infinity, we'll be able to figure out our results, right? So for any particular value t, for any positive value to the right of 1t, then this would be our integral. When we find the antiderivative of 1 over x squared, we get that it's just negative 1 over x, right? The derivative of this is equal to this. And now when we apply our limits, we end up with 1 over t, the minus here, minus, and then there's a little minus that gets distributed, so it becomes plus 1 over 1. Flip that around and we get this. Right. Here, let me, whoa. Make sure that this part here is clear. Oops. Just making sure that this part here is clear. That this is the same thing as negative 1, and then we end up with 1 over t minus 1 over 1. And then as we distribute this minus 1, we end up with this, positive 1 minus 1 over t. Right? And so this is valid for any value t, such as this guy right here. Here's our t value. So if we stop anywhere, then we would end up with this as our answer. Right? So then once we have that, all we have to do is let t go out to infinity, and we'll be able to figure out the area as this goes out to infinity. Notice that a of t, the area of t, is less than 1 no matter how large t is chosen. Right? Because if we look at the equation we end up with 1 minus this fraction, which gets smaller and smaller and smaller as t goes out to infinity, right? It's always a positive number but it keeps getting smaller and smaller and smaller. Here's some examples of what that area would be. If t is 2, then this little formula right here. If t is 2, then we know that this is going to end up being 1 over 1 minus 2, which equals to 1/2. If t is 3, this is when t equals to 2. When t equals to 3, we end up with 1 minus 1 over 3, 1/3, which is equal to 2/3. 2/3. Right? When t equals 5, we get that the whole area equals to 1 minus 1 over 5, which is then going to be equal to 4/5. Right? So for any specific value of t, we can get the exact area. So all we have to do now is let t go to infinity, and we get our answer. And when we do that, we see that the area equals to 1. Are there any questions about this? No? 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 This is similar, related to this other problem. Come on. Maybe back when you first learned about limits, a classic way to learn about them is to think about our pi. We have a pi, one whole pi, right? One whole pi. And we decide that on day number 1, we're going to eat half of our pie. So day 1, we eat half our pie. And then over on day 2, we eat half of what we have left over, right? We have half a pie left over, and we eat half of our half, which means we really eat a fourth, right? On day 2, we eat 1/4 of our pie. And then on day 3, we come back and we eat half of the fourth, and half of the fourth is 1/8, right? So day number 3, we eat 1/8, and then keep going in that pattern. And then day number 4, we eat half of what we have left over. So half of an eighth is going to be 1/16 from day number 4. And then we keep going and going in that pattern. Day number 4, we get 1/16 of our pie. Now I know that in reality, eventually you run out of pie, but mathematically we could just keep going forever, right? So let's establish a pattern for these guys. First of all, I could see that another way of rewriting this would be equal to 1/2 and 1 to the power of 2 and 1 over 2 to the power of 3 and 1 over 2 to the power of 4. So we start to see a nice little pattern that on day 4, it's 2 to the 4 in the denominator. Day 3, it's 2 to the power of 3. So on day n, this is going to be equal to 1 over 2 to the power of n, is how much pie we eat on the nth day. Okay, so that pattern continues. And now if we think about the whole thing, how much are the running sum of what you've eaten? So it's going to be a partial sum situation. So s sub 1 is just going to be equal to our half. And then s sub 2 is equal to 1/2, come on, 1/2 plus 1/4. Right, common denominator is going to be 4, so we need to multiply this by a 2 over a 2. So really we get 2 over 2, 2 over 4, which then becomes 3 over 4. Come on, we get 3 over 4. On day 3, we have 1/2 plus the 1/4 plus the 1/8. Right? So now we get a common denominator of 8. We're going to multiply this, 2 over 2, multiply this, 4 over 4. And so we get 4 plus 2 makes it 6, plus 1 makes it 7. So we get 7 out of 8. Okay. On day 4, we get that this is going to be the day we ate half, and then also we ate a fourth, and then also we ate an eighth, and then also we ate a 16th. Right? The running total, the partial sum. Common denominator in this case is going to be 16, so multiply this by 2 over 2. Multiply this by 4 over 4. Multiply this guy by 8 over 8. So they'll all have 16 in the denominator. And so this will end up being 8 plus 4 makes it 12, 14, 15. 15 over 16. And again, if we want to establish a pattern, I could see that the denominator is also going to be powers of 2. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. And the numerator is always one smaller than the denominator. So following that, I could see that the nth term, just by following that pattern, is going to be 2 to the nth, and then this is going to be 2 to the n minus 1. Okay. In other words, I could have rewritten this guy as 2 to the 4th, right? Because it's the 4th partial sum. 2 to the 4th, that gives me 16. And the numerator is 1 less than the denominator. 2 to the 4th minus 1 is 15. Good. And this one, the denominator, I could have rewritten as 2 to the 3rd. And the numerator is 2 to the 3rd minus 1. 7. Good. This one is 2 to the 2nd, and this one is 2 to the 2nd minus 1. So it follows this pattern. Good. Good. This can also be simplified to be rewritten as 2 to the n over 2 to the n minus 1 over 2 to the n, which is also known as 1 minus 1 over 2 to the power of n. Good, so this little formula tells you how much is the running total of all the pie you've eaten as a function of n. So if they ask you how much pie have you eaten by the 12th day, that would be the 12th partial sum. And instead of adding up all those small fractions, I could say that this is equal to 1 minus 1 over 2 to the power of 12. Okay. I can just get my dandy little calculator here. Now, 2 to the power of 12 is equal to 4096. This is 1 minus 1 over 4096. So this will be equal to 4095 over 4096 as a ratio of the pi. So almost all of it. There's very little pi left at this point, right? Good, 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 good. Okay, so when we have a function of n like this, then for any specific value you choose, you're going to get a result. But now if we think about the limit as n goes to infinity of 1 minus 1 over 2 to the nth power, right? This is the limit. Oops. This is the limit as n goes to infinity of s sub n, the partial sums. As this goes to infinity, we see that this part here is going to go to infinity in the denominator. 1 over a value that's getting infinitely large becomes infinitely small. So this whole thing goes to 0. So we know that this part is going to go to 0. And so the whole thing equals to 1. Which would make sense because we started out the whole process by saying let's start off with 1 whole pie, and then you start eating it in a particular manner, half now, half tomorrow, then the other half, then the other half, then the other half. It would make sense that as we keep going around the pie here, as we start eating day 1, day 2, day 3, day 4, as we keep going, eventually we're going to have one whole pie. But if we ever stop at any specific nth value, we haven't gotten to the whole pie. We might be really close to it, so we can get approximately the whole thing if we stop at any specific value of n, but we won't get all of it. On the other hand, since the limit, we were able to find the limit in this case, and the limit equals to 1, that means that it is exactly 1, right? This is not an approximation. The result is 1. That means that that entire result is a 1. Good? Questions, 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 questions? Okay, so going back to this guy over here, we wanted to find the area in blue here, trapped between 1 to t, this value here. So if t is some constant, some place we stop, then we're going to get an area based on that value. So if t is a 2, then we get that the area trapped right in there is a half. If t is a 3, we get that that area in there is 2/3, and so on and so forth. But then when we evaluated our result by letting the limit t go to infinity, we got that the answer was 1. That means that that exact area, as this goes all the way out to infinity, that whole area is just equal to 1. Right? It's not approximately 1, it is 1. Good. Questions, questions, questions? If you have like a little sister or a nephew or somebody who's turning 1, you can put this on their birthday cake. It is exactly 1. Right? This right here. Happy limit as t goes to infinity of 1 minus 1 over t. Right? That is 1. Questions?
Hello, Professor?
Yes.
So t cannot equal 1?
T cannot equal to 1. Oh, okay. So, we're finding the area between 1 and something over there. So if we let t equal to 1, we're going to get a 0, right? So it's just kind of a silly question, right? It would just be a simple answer if we let it be that. It would just be the integral from 1 to 1 of this. So we would just get a 0. Right?
But that could be a possible answer. It would be correct if that was asked.
Sure.
I know you said it was silly, but that could be an answer.
Absolutely, sure. The integral from 1 to 1 of 1 over x squared dx equals 0. Mm-hmm. Cool.
Thank you.
Sure. Any other questions on this? So we're going to deal with, in this section, we're going to deal with cases like this, where we have an infinite symbol there. We want to find out the area underneath the curvature trapped between some function that is positive and the x-axis, as one of the limits, or maybe both the limits, go out to either positive infinity or negative infinity. And the way we deal with it is to do kind of a two-part thing. We first replace the infinity symbol by a constant so that we can integrate it up to some constant, and assuming that that part works, we're going to end up with some new function of that variable. T is very popular. And then we're going to let t go either to positive infinity or negative infinity. And if that limit exists, then we say that the integral is defined. It's convergent. Good. If that limit does not exist, then we say that that integral is divergent. Good. So using this example as a guide, we define the interval of f over an infinite interval as the limit of the integrals over finite intervals. Right? So we take that infinite interval, we define it momentarily in a finite interval, and then we take the limit, we apply a limit to that in order to be able to figure out what the area over the infinite interval would be. Good. So the integral from some constant a to positive infinity of f of x dx, we're going to replace that infinity symbol with some temporary placeholder value t, and then we take the limit as t goes to infinity, and then if that limit exists, provided that limit exists as a finite number, we would say that this this improper integral exists. This improper integral exists. It's convergent. Good. We could also go in the other direction. So if we have the integral from negative infinity up to some value b of f of x dx, then the limit as t goes to negative infinity, right? So we're going to push this guy out to negative infinity of f of x dx is going to give you the same result, provided that it exists. Good. So the improper integrals from a to infinity f of x dx and from negative infinity to b f of x dx are called convergent if the corresponding limits exist and divergent if they don't exist. And now if we had something like this, where we're integrating some function from negative infinity to positive infinity, then we just break them up into two pieces, where we can just arbitrarily choose some convenient constant value of a. 0 is very popular, but also it could be 1 or any other convenient value. So we're just breaking it up into two pieces, and so now if we can figure out what this integral is, again by applying a limit, we can figure out what this integral is, again by applying a limit. Then if both of them exist and they equal some constant value, then we can just add them together, and then that'll be the result to this thing. Does that make sense? This is very popular in statistics. If any of you guys have taken statistics, in statistics we very often work with functions that look like this. Right, so a function that goes this way and then has a nice little bump and then comes back this way. Something like that. We say these are normal functions. And so they have the characteristic that this is going to go out to positive infinity and this is going to go out to negative infinity. The function always gets infinitely close to the x-axis in either direction. And we need the whole area, right? We're always interested in the area underneath the function. So figuring out these kinds of areas is very important in statistics. Okay. So we would need to figure out an equation for this part here. And if you've had statistics, you know it's an ugly equation. So I'm not going to attempt to write it down. Let's just say it's some function g of x. And so now we'd say that the area in red, is equal to the integral of g of x dx starting from negative infinity up through positive infinity. If you can establish what that is, then you'd find an equation or an area for this function down here. Good? Questions? Okay. Any of the improper intervals in definition 1 can be interpreted as an area provided f is a positive function. Right? So we can do this interpretation of area in many applications when we think of them as positive functions. For instance, in the case where f of x is greater than 0 on the interval from a to infinity f of x dx is convergent, then we define the area of the region S, which is this. Let me see if I can zoom in a little more. The region S as this, right? So we have a domain that starts off at a and shoots off to infinity. This is the integral from a to infinity of f of x. F of x is this root function here. And the way it's drawn, f of x is positive. So it's the area trapped above the x-axis, below that function. This blue part here is the area, right? So we consider it, we can think of it as an area. Good. Any questions so far? Any questions so far? Okay, so let's do this guy. Determine whether this integral from 1 to infinity of 1 over x dx is convergent or divergent. Okay. So I know it's tempting to skip this part, but it is important to include it because it does mean something. So we want to say that this is equivalent to the integral from 1 to something. Now t is very popular, but I don't like using t because my t's look like plus symbols. So we can choose anything, it doesn't matter. I'm going to let it be w. I like w. So we're going to go from 1 to w of 1 over x dx, and then we also have to apply the limit as w goes out to positive infinity. Right? So if we think of a little picture to kind of go with this, 1 over x is going to look like this, sort of, only less ugly, of course. And then over here, it kind of goes like this. So this is the function f of x equals to 1 over x. And we're interested in the integral that goes from 1 to infinity. It's supposed to be like that. So we're interested in something that goes like this forever. And so what we're going to do is stop at some value w. So where w is greater than 1. And figure out what this answer is as an equation of w. And then we're going to apply the limit as w goes to infinity. Good. This is where w is strictly greater than 1. Well, greater than or equal to 1. But we know that when w equals to 1, we know we're going to get a 0. But we're interested in large values of w, right? That's the whole point. We want to apply the limit so that this goes that way and goes off to infinity. Good. Okay, so now we try and find this integral. So now we're just focusing on this part by itself here, figuring out what that is. And well, that's just going to be ln, right? This is equal to the limit as w goes to positive infinity of, and this is just going to be the limit ln of absolute value of x evaluated from 1 to w, okay, which will be the limit as w goes to infinity of ln of w, come on, ln of absolute value of w minus ln of absolute value of 1. ln of 1 is 0, so we don't have to worry about that. And so we just need to figure out what this is. ln as w goes to infinity, right? And we definitely know that it's greater than 1. So let's think about what the ln function looks like. The ln function looks like this. ln of x looks like this, where this is the x variable, and it goes right here at 1, at 1 equals to 0. Now we said w was definitely greater than, you know what, we should just stick to strictly greater than 1, just because we're interested in very large values. So for w being strictly greater than 1, right, we create a little area, and we're interested in that pattern. So when it's greater than 1, then this absolute value is redundant. I don't need absolute values because this part is always positive. So I can just simplify it and just say that it's ln of w, so I don't have to worry about this absolute value part. Okay, so here is the graph, ln of w, ln of x. It's just a dummy variable, right? But this is the graph. This is the pattern. And so as the input to the ln function, as that input goes off to infinity, then this output here, I shouldn't have put an A, I meant to put in. As the input goes out to positive infinity, right? The larger that input goes, the output goes up to positive infinity. So this whole thing just goes out to positive infinity. It grows without bound. Just keeps growing and growing and growing. Good. And so because this was not equal to some finite number, it diverges. Right? So this integral diverges. Any questions? No? No? No?
Wait, why does it diverge?
So ln of the input, right? Ln of x, ln of w, whatever, is this graph. Maybe it would have helped if I put it as a w. Come on, erase. So x is just a dummy variable, so I could use x, I could use w, whatever. So the input, is this way. As the input gets larger and larger and larger, the output gets larger and larger and larger. It never stops growing, right? So it goes off to infinity. So that's what this is.
Oh, okay.
Right? This ln of w, the limit as w goes off to infinity, then that whole thing goes off to infinity. It doesn't equal any constants. Good? Questions? So when we come back and think about the area from 1 out to infinity, right? We were actually interested in this whole area in green, all the way out to infinity, forever. And well, that area is infinite. It is not equal to some constant. That's what we discovered. This area in green is infinitely large. It doesn't converge to anything. Now, it looks very similar to the other case, right? So if we compare the two, what just happened? Okay, so the author did the same thing I did. That's what the author did. Pretty much the same thing I did. Only neater. Okay, let's compare the two that we've looked at so far. One of them was this 1 over x squared dx that looked like this, and we wanted to find that area, and we found that it converged, and we found that it equaled to 1. Right? That was that first example I went over. And then we just finished going over this example, which is the integral from 1 to infinity of 1 over x dx, and we found that this one diverges. The only difference between these two integrals is that here we have a 2, this is x to the power of 2, and here we have a 1, right? This is x to the power of 1, right? It's the same integral from 1 to infinity, and so the graphs look very, very similar. Here is the graph of 1 over x, the area from 1 to infinity. We found that this whole area here diverges. It's infinite, infinitely large, right? Infinite area. Whereas this one, that is 1 over x squared, very, very similar looking, but yet we find that this whole area going out to infinity is just equal to 1. 1 unit, whatever units we're working with. 1 foot, 1 meter, well, squared, right, since it's an area. Good. So, kind of weird. They look very, very similar, but this is an infinite area, and this one is an area that equals to 1 unit. Good. So, it's important to note that the difference is that this function squeezes toward the x-axis fast enough to be able to trap out an area. This one does go toward the x-axis, but in a much slower way, and it allows too much area to be trapped in between here, and so it has an infinite amount of area. So here's a case where it not only does it matter that the function squeezed down to the x-axis, but it has to go there fast enough, right? Because if the function didn't go down to the x-axis, that would be an even easier question, right? If I told you, here is this function and it's doing this, like that, forever, find the area that goes from 1 to infinity underneath that, well, that one's easy. I don't have to do anything. I know that this whole area is going to be infinite. Come on. Right? If the roof here is just going off to infinity, and this is going off to infinity, then the whole area is going to be infinite, right? That's a no-brainer. Even if the roof line here was just kind of flat, that would also be kind of a silly question, right? Easy answer. If this thing was just a constant this way, just a flat constant, and I want to know the area trapped underneath there from 1 to infinity, well, that's also an easy answer. It's also going to be infinite. Right? So it's pretty clear that as long as we're looking at the cases where the domain here is from a constant out to infinity, then in order for us to have a chance for this to be a constant and not an infinite answer, I need this function to go toward the x-axis, right? I need to squeeze in so that we have a chance to be able to say, oh yeah, that whole thing just equals a constant. But that's not good enough, because here we have a case where it does squeeze in and go toward the x-axis, but it's still not good enough. So not only does it have to squeeze in toward the x-axis, but it has to go there fast enough to be able to do it, like in this case. Good. Questions, 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 questions? No, no, no. So just based on this, you can easily get some answers to say something like this: 1 to infinity of x to the 7th power plus 2x squared dx. Don't even waste your breath. This thing is growing, right, for positive answers. This thing is just going to be growing. This is always positive. For positive inputs, this is always positive. This whole thing is just growing. And I want to know the area from 1 to infinity. This is just going to be infinite. Right? The only way I have a chance to potentially get a constant as an answer is if this function is converging down to 0 as the inputs grow toward positive infinity. And even then, it might not be enough. I need it to go down to 0 fast. Geometrically, this says that although the curves y equals to 1 over x and y equals to 1 over x squared and y equals to 1 over x look very similar for x greater than 0, the region under y equals to 1 over x squared to the right of x equals to 1, the shaded region in figure 4, has a finite area, whereas the corresponding region, okay, this is saying everything I've just said. Value does not for the integral. This leads to this. Well, why don't we? Let's just give it to me. I don't like that. Let's figure out what this is here. Come on. So let's look at this guy here. The integral from 1 to infinity of 1 over x to the power of p dx, right? So this is where p is some constant, where p equals a constant, right? So keep in mind the x is the variable of integration. Okay, so we're gonna first of all say like, okay, let's get rid of that infinity symbol there. Let's go back to, how about n? The limit as n goes to infinity of the integral from 1 to n of 1 over x to the p dx. Okay. So this is the same thing as the limit as n goes to infinity of the integral from 1 to n of x to the negative p power dx, right? I just rewrote 1 over x to the p as x to the negative p power, which is then going to give me that that's equal to the limit as n goes to infinity of, and this is going to be equal to x to the negative p power plus 1 plus 1. So if you think about how do you know, it's kind of a guess and check game here. If I think of the derivative of this, I would bring that exponent out in front and then subtract 1 from the exponent, which would give me that minus p. So then to get rid of that constant that you bring out in front, you divide it by negative p plus 1. Good. And all of that gets evaluated from 1 to n. So this is going to be the limit as n goes to infinity of, what do we do here? So let's make this n, so that would be x, oops, not x. That would be n to the power of minus p plus 1 over minus p plus 1 minus, and then this is 1 to the power of minus p plus 1 over minus p plus 1. Okay, and let's see, what do we want to do? We want to switch around these guys to simplify it. It looks a little nicer if we flip these around and say that this is n to the power of 1 minus p all over 1 minus p, and minus 1 to the power of 1 minus p all over 1 minus p, just flipping around these things. Okay, and now I want to kind of solve this by breaking it up into two cases. Case number 1 is when p is less than 1, equal to or less than 1, and then think about the case when it's greater than or equal to 1. And the reason I'm choosing 1 is because that's where this is going to be equal to 0, and then that's the decider between a negative exponent and a positive exponent. So let's, to solve this whole thing here, this is considering for all p's, but I'm going to break it up into pieces and think about the case when p is strictly smaller than 1, less than 1, well, maybe less than or equal to 1 to give me the 0. Strictly less than or equal to 1, then you would end up with the limit as n goes to infinity of n to the power of 1 minus p all over 1 minus p minus 1 to the power of 1 minus p all over 1 minus p Okay, so for P, strictly no, less than or equal to 1, then considering this, right? So this is when P is a little smaller than 1, just a tiny little bit smaller than 1. So if it's just a little smaller than 1, then 1 minus, I'll put that here, for P being strictly less than or equal to 1, then 1 minus a value that's a little bit smaller than 1 is going to be greater than 0. Good. So this is going to be something a little bit bigger than 0. It's just going to be 1. So this is just going to be minus some constant. So 1 to the power of anything is just 1. 1 over this guy is just going to be some constant. So this doesn't really have a huge impact on my final output. But this guy is really the thing that dominates what's going to happen with my result. And n to the power of some small positive decimal, some positive exponent, is going to shoot off to infinity, right? Think of n squared, for example, or n to the 1/2 power, right? N to the cubed power, right? Anytime we have an exponent that is positive, the graph will shoot off to infinity. Good. So this whole limit is going to be equal to infinity. The limit as n goes to infinity of n to the 1 minus p over 1 minus p minus 1 over 1 minus p, the whole thing just shoots off to infinity. Is that okay? Questions, 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 questions? On the other hand, if p is strictly greater than 1, then the limit, if we study the limit as n goes to infinity of n to the 1 minus p over 1 minus p minus 1 to the 1 minus p over 1 minus p. Okay, so if p is strictly greater than 1, strictly greater than 1, a little bit bigger than 1, then 1 minus p is going to be a little bit less than 0, right? If this one's a little bit bigger than 1 or bigger than 1 for sure, then 1 minus this number, this one's going to be bigger than 1. So the whole thing is definitely less than 0, right? So that means that these exponents are all negatives. Well, again, this is just going to be 1. 1 raised to 20 power is 1. And this is some constant. It doesn't really matter. It's not going to have a huge impact no matter what it is. It's just a constant. This is what will really determine what's going to happen to my graph. And anytime we have n to the power of a negative exponent, what do? We flip that negative and rewrite it as 1 over n to the power of a positive exponent. Like, for example, if we had n to the negative third power, that's 1 over n to the positive third power. So that means that this whole thing is going to converge. Right? It's going to go towards 0, in fact, as n goes to infinity. Good. So the limit as n goes to infinity of n to the 1 minus p, just that part there, all over 1 minus p. Right? So that's just some constant. It doesn't matter. It's not being affected by the n. This, for the case where p is definitely greater than 1, is going to be equal to the limit as n goes to infinity of, well, this is definitely a negative, so we put it in the denominator. It's going to look ugly no matter what I do. Whatever, I'll just put negative exponent. Negative exponent over 1 minus p. And so this whole thing goes to 0 as n goes to infinity. Good. And then we'll be left with some constant. Good. So it converges. And that's where you get this thing here, that if we have this integral here, then it converges if p is greater than 1, strictly greater than 1, and diverges if p is less than or equal to 1. Does that make sense? Questions, 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 questions? Pretty much good. Okay, let's keep going then. The other case we're going to run into is cases where there's a vertical asymptote for our function. So suppose f is a positive continuous function defined on a finite interval from a to b inclusive of a but not b, but has vertical asymptote at b. So let S be the unbound region under the graph of S and above the x-axis between A and B. So we want to find this whole area from A to B, including the fact that the function gets infinitely close to that vertical asymptote, right? They shoot off to infinity. So we want to find the entire area of the whole thing. And similar to before, what we're going to do is we're going to, first of all, cut it off before by some constant value that's trapped between A and B, ideally close to B. And we're going to find an area for this finite part, right? So it doesn't shoot off before it shoots off to infinity. We're going to get a function of t, this variable, and then we're going to apply the limit as t goes toward b from the left-hand side. And if that limit exists and it's equal to a finite value, then we would say that that whole area from a to t of f of x dx is convergent. It exists. Make sense? Questions, 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 questions? Good. So if it happens that a of t approaches a definite number a as t approaches b from the left-hand side, then we say that the area of the region S is a, and we can write that the integral from a to b of f of x dx is equal to the limit as t approaches b from the left-hand side of a to t f of x dx. We use this equation to define improper integrals of type 2, even when f is not a positive function, no matter what type of discontinuity f has at b. Okay, this is the trickiest one, or the one that tricks people the most, because it's not easy to spot that there's a problem with it. In the other ones, when you're given something like this, when you're given, let's come back up here. When you're given this to integrate, well, right away you spot that there's something interesting about this integral because you see the infinity symbol there, or you might see a negative infinity symbol in the denominator, or both. So it's easy to spot that we have an improper integral, and so people take steps to fix it. But as a caution, these other types of problems They're not always easy to spot because the original integral might look innocent and might look like there's nothing wrong, but it's going to be up to you to realize that there is a vertical asymptote, right? There is a place where this function is undefined, and that vertical asymptote is somewhere in this little domain from A to B. Okay, so when you run into that, you have to break up the integral so that we have a region where the function is defined by some constant, usually t, or it could be any other dummy variable, and then apply the corresponding limit to be able to get the area you want. Okay, so similar in the other direction. If there is a vertical asymptote at A, then we want to find the area between, we want to find the integral from A to B of f of x dx. We again replace the variable A by some temporary placeholder variable. T is very popular. Find the integral from T to B of f of x dx, assuming that there are no other problems in this region. So f of x is continuous and integrable in that little region. Once we find an answer to this, we'll get a function of t. Then we apply this limit as t approaches a from the right-hand side and get our answer from there. Good. The improper integral from a to b f of x is called convergent if the corresponding limits exist, and divergent if its limits do not exist. If f has a discontinuity c, where c is somewhere in the middle, not on the outer bounds, then we're just going to have to break up the integral into two integrals and then find the answers for each of them separately. And if they both exist, then we can add them together, and then that would be the answer to this one. And then we'd say that this integral is convergent. If one or both of these fail, then we wouldn't be able to get a finite answer for this, and we'd say that this integral is divergent. Good. Okay, so here's an example, and as I said, this might look like a nice innocent little example. Might not be able to spot that there's anything wrong with it, but we have to be diligent when we're looking at these and make sure that our function doesn't have an undefined somewhere. So if we pay attention for a little bit, we notice that when x equals to 2, we have a problem, right? So when x equals to 2, then f of 2 equals to 1 over 2 minus 2 square root of 2, which is equal to 1 over 0, which is undefined, right? So we're not allowed to integrate that. Even though it's tempting to just find the answer and plug it in, and that's fine, that's not going to be the answer, because this is undefined at the value of 2. Good. Okay, so what we have to do is replace the 2 with a constant, right? Looking at the domain. Forget for a second what the roof of this function looks like. We have our domain, our x value domain. X goes this way. And we're trying to integrate from, here's 0, and here is 1, well, let's say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so we want to integrate from 5 all the way down to 2. All the way down to 2. So we're going to momentarily find some variable there. Let's call it, where is it? I'll stick with w. Let's call it w. So we're going to find the integral from w to 5, and then assuming that we can find the answer to that, then we're going to find the limit as w approaches 2 from the right-hand side. Good. So we're going to say that this guy is equivalent to the integral from w to 5 of 1 over the square root of x minus 2 dx, and then we got to throw in there the limit as w approaches to 2 from the right-hand side. Good. Okay, well, that's really the hard part in this section because the actual integral is not that hard. Compared to the really ugly integrals we've been solving, this one isn't bad at all. So if we think of this as the root, you can just kind of do a little bit of a guess and check. This is just going to be square root of x minus 2, right? So if you think of this as x minus 2 to the power of positive 1/2, when we take its derivative of this function is going to be 1 over 2 times x minus 2 to the negative 1/2, right? Bring down the exponents, subtract 1, we get that. So that means we get 1 over 2 square root of x minus 2. And with the chain function, we'd find the derivative of the inside part, which is just going to be 1, so times 1. So we're almost there. The derivative of this is almost that, except we got to get rid of that constant, so we got to throw in an extra 2 there. And now I can say that the derivative of this is exactly that. Right? So this gets evaluated as x ranges from w to 5. And so this is going to be the limit as w approaches 2 from the right-hand side of 2 times the square root of 5 minus 2 square root of w minus 2. Good, 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 good. So we end up with 2 square root of 3. That's not affected by w, right? There's no w variable in there at all. So that's just going to be 2 root 3 minus 2 times the limit as w approaches 2 from the right-hand side of the square root of w minus 2. And now it becomes important that we kept track of this from the right-hand side thing. From the right-hand side means that it's always going to be a value that's a little bit bigger than 2. Right? As we're approaching 2, we're approaching it from this direction, so it's going to be 2.01, 2.001, 2.000001. Right? It's getting really close to 2, but it's always a little bit bigger than 2. So if it's always a little bit bigger than 2, that guarantees that this is always a little bit bigger than 0. Right? W approaching 2 from the right-hand side means w is always a little bit bigger than 2, which means that w minus 2 is always a little bit bigger than 0, which means that this is getting infinitely close to 0, but always positive, and so the whole thing is just going to converge to 0. That's important because remember that if this was ever allowed to be a negative, we'd have the even root of a negative, we'd have an imaginary number, and then we'd have problems. But in this case, it all simplified to just being a nice little answer of 2 root 3. Good. Questions, 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 questions? No? Right, let's see. 2 root 3, yay. It comes with a nice picture too. So here's a nice graph of that function. And notice that the function y equals to 1 over the square root of x minus 2 looks like this. And there's a vertical asymptote at x equals to 2, so that this function gets infinitely close to it and shoots off toward y goes toward positive infinity in this direction. Right? So there's always a little gap here. There's an infinite amount of space that's always there. But even though this shoots off to infinity, the whole thing does converge. The area, starting from here, going that way, even though there's a little hole here that goes off to infinity here, infinitely high, that whole area is just 2 root 3. Good. Questions, questions, questions? No? All right. Okay, the last concept in this chapter is this idea about the comparison tests for improper integrals. So the comparison test for improper integrals, sometimes it's impossible to find the exact value of an improper integral, and yet it is important to know whether it converges or diverges. In such cases, the following theorem is useful. Although we stated for type 1 integrals, a similar theorem is true for type 2 integrals. So the comparison test states that suppose that f and g are continuous functions such that f of x is always greater than or equal to g of x, which is always greater than or equal to 0. So we're looking at cases where they're both positive, but the f of x one is always bigger than or equal to g of x. And we're looking at cases for x being greater than or equal to a, some constant a. Then we have that if the integral from a to infinity of f of x dx converges, so if the bigger one converges, then we can conclude that the one that's always equal to or smaller also converges. Or the other way around, if the smaller one diverges, goes off to infinity, then the one that's always greater than or equal to also diverges. Good. So here's a nice picture of that whole process. Right, so here is just the visual. We have a case where the f function is always bigger than the g function, bigger than or equal to the g function, and they're both always positive, so they're both above the x-axis. And so we can conclude two different things, right? As we're finding these two areas, one of the areas is the area underneath the g function, and the other area is the area underneath the f function. So if I can conclude that the g function is infinity under here, if I can show that the area under the g function is infinite and the f function is always bigger, then I can conclude that this one's also infinite, right? That's divergent. If the smaller one diverges, then the bigger one must also diverge. Good? Good. And then the opposite of that is, given the same situation, come on. Okay, it's not letting me do that. Oh, there we go. Okay. And then the other case is, what if we were interested in finding the area, or we're comparing them, and we found out that the area of the larger one definitely converges, right? This whole area in green is equal to some finite number. Should say, I don't know. This whole area in green going out to infinity. Let's say that I do some work and I figure out that that whole area is finite. Maybe it equals 7. After all that work, I figure out that going out from a out to infinity, it equals 7. Well, then the smaller one must also be finite. It might not be 7. It might be something smaller. It's going to have to be something equal to or smaller than 7, but it's going to be convergent, right? So if the larger one is convergent, then the smaller one must also be convergent. Is that clear on this? Any questions? No? So the way we're going to use this comparison test is that we're going to be presented with some integral. It's going to be pretty ugly, and you're going to have to maybe kind of have some instinct as to whether you think it converges or diverges. If you think it diverges, then you're going to have to come up with some other simpler function such that that simpler function is always smaller, yet that simpler function diverges. That way we can use part B here to simplify it and get to a conclusion that it must diverge. Or if you suspect that it converges, then you must think of another simpler looking function such that that simpler function is always strictly greater than the one you're working with, and that greater one converges. Therefore, that means your function converges. So this one is these kinds of problems are really tough because you have to be very creative to come up with something that will work, right? So if the area under g of x is infinite, then so is the area of f of x. Note that the reverse is not necessarily true, okay? So the reverse is not necessarily true. If I can figure out that g of x converges, the smaller one converges, then I don't know what's going on with the larger one. Maybe the larger one also converges, maybe it doesn't. Same with the other way around. If the bigger one diverges, then that doesn't tell me anything about the smaller one. Maybe the smaller one also diverges, maybe the smaller one converges, right? So it only works when I could see that the smaller one diverges. That must mean that the larger one also diverges. Or if the larger one converges, then the smaller one must also converge. Good. All right, so here's an example. That is pretty ugly for sure. Pretty ugly right there. Figuring out what that is, right? So luckily they're not asking me to actually find an answer. They just want me to at least conclude, show that. In fact, they're even telling me, so it's even nicer than that. They're just telling me to show that it converges. Show that it converges. So in order to show that this guy converges, it would be nice if I found a function that was always bigger than this one, and yet that bigger one converged. That way I can say, yep, the smaller one must also converge. Good. Okay, so what to compare it to? And this is from 0 to infinity. So we're looking at the positives. For the positives, let's think about the fact that for x greater than 1, so if we kind of break it up for greater than 1, then it must be true that x squared is greater than x. That's true for anything bigger than 1. So like if x is 2, if x is 3, if x is 4, squaring it is always going to give you a number that's bigger than that guy. And now if we multiply both sides by this minus sign, then that means that minus 1 times x squared is always going to be less than minus 1 times x. And that's what that guy is. So now e to the minus x squared is always less than e to the minus x. Right? Well, I can always slap on the equals too, but x is greater than, for x strictly greater than 1. I mean, I can also toss in the greater than or equal to here. Greater than, if x is greater than or equal to 1, then x squared is greater than or equal to x, which means that this is less than or equal to, right? In cases of 1, they equal each other. And this is less than or equal to that. So on the number line, right, without really graphing each of these, I've just established that on the number line starting at 1 out to infinity, it must be true that this function here, whatever it looks like, e to the negative x is always bigger than or equal to this function, whatever it is. So I'm just drawing something. It doesn't really matter what it looks like. I'm just saying it might look like this. It might be that it equals to it in a couple of spots, but other than that, it's always smaller. E to the minus x squared. Good. And they're both always positive. Right? That's also important to note. They're both, this one is less than that one, but they're both greater than 0. Good, good. Remember that whenever we have a little minus in the exponent, that doesn't mean that our result is negative. Like e to the second power, that's a positive number. And then e to the negative 3 power, that's equal to 1 over e to the positive 3 power, and that's also a positive number. Right, so these are all positive numbers. Good. Okay, so now that I have a simpler function to compare it to, if I can show that the blue one, going out to infinity, that this blue one converges, the area underneath the whole blue is equal to some constant, then that's enough to conclude that the smaller one must also converge. Good. Okay, so that's what I'm on a mission to do now. So now let's figure out the integral. The integral from from 0 to infinity. Integral from 0 to infinity of e to the minus x dx. So I'm going to break this up into two pieces and say that this is the same thing as the integral from 0 to 1 of e to the minus x dx plus the integral from 1 to infinity of e to the minus x dx. That's really what I needed. So actually I didn't really need the 0 to infinity, I just really needed this. Yeah, so actually let's restate this one. So e to the minus x squared, so I'm looking at this original one. So the integral from 0 to infinity of e to the minus x squared dx is equivalent to this. Good. And now this is the tricky part. This is what I'm not really sure about as this goes on to infinity. This is just going to be some constant, right? Some constant that doesn't really affect me. Oops, there's a 2 there. But this one is the one I care about. So what I want to do is use the comparison test on this guy so I can figure out what happens to this one. And then that's where this comes into play. Right? And the reason I had to break it up from 0 to 1 and 1 to infinity is because this statement here is only true for values of x that are greater than or equal to 1. Good. If we try and take like 1/2, 1/2 squared is less than 1/2. So it would be in the other direction for values between 0 and 1. Okay. So this one is kind of tidally locked with this function of e to the negative x. If e to the negative x converges, then so will this one. Good. All right, so now we go off to the side here and think about what that function is. The integral from 1 to infinity of e to the minus x dx. Okay, well that guy we're going to say, well that's equal to the limit as w goes off to infinity of the integral from 1 to w of e to the minus x dx. And luckily this is a nice, easy one to figure out. This is the limit as w goes to infinity of -1 times e to the negative x. The derivative of this is to copy it, times the chain rule would give you an extra -1, so that means we have to multiply by a -1 out there. Evaluate it from 1 to w. So this would be equal to -1 times e to the minus w minus -1 times e to the -1. And then this is the limit as w goes to infinity of this whole thing. So we can simplify that a little bit. That's going to be a plus there. So the limit as w goes to infinity of -e to the minus w plus e to the -1, which I can flip around. This is just going to be 1 over e minus, that's an e, 1 over e minus the limit as w goes to infinity of 1 over e to the w. And so this whole thing goes to 0. E to the w power as w goes to infinity is going to go off to positive infinity. 1 over that goes off to 0. So the whole thing just becomes 1 over e. Good. So I've established that this equals 1 over e. Good, good, good. So really what I've established is that this converges. Any questions? No. Okay, so then therefore by the comparison test I can conclude that because the larger one converges, it must mean that the smaller one must also converge. So I can conclude that this converges. Good. Questions? Good. Now, this is just going to be some constant. So some whole number, some constant here. There's no infinities, right? This is just some function. It's not going to have anything special going on with it. There's no vertical asymptotes, nothing like that. I'm just integrating from 0 to 1. So it doesn't really matter what the answer is. I just know that it's going to have some answer. It's going to be some area, right? So what happens with this thing is just it kind of shoots up that way. The only reason I broke it up is because when we're between 0 and 1, this thing might kind of switch roles where this one ends up being smaller than that one for a little bit. But it doesn't really matter at all. I'm just saying this is just some area that happens there. And so therefore the entire thing is going to be convergent. Right? And that's what they wanted me to prove. So the tricky part is showing that this thing that goes off to infinity, this integral, is going to converge. Any questions? Comments, questions, issues? No? So kind of reverse this guy, and then this leads me to that. No questions. see what the book did about that 0 to 1 thing. We can evaluate directly because the antiderivative is not an elementary function. We can write this as that. And observe that the first integral on the right-hand side is just an ordinary definite integral. Just an ordinary integral, right? Oh, okay, so they actually graphed it, and this is what it looks like. So here is e to the minus x squared is this red one, and then e to the minus x is this blue one. So for at exactly 1, they equal each other, and they kind of switch roles. For 1 toward positive infinity, it's always true that this one is the larger one, right? The e to the negative x is always larger. Good. But then they kind of flip roles between 0 and 1, and the other way is true. Good. So notice that over here, the area underneath the red over here is some constant. I can see it, I can visualize it, but I don't even need the answer. They're not asking me to find the actual area, they're just asking me to consider whether it's going to converge or diverge. So this part definitely converges, it's some constant. It's a trivial area of some kind, some constant. The tricky part is to establish whether the area over here is going to converge or not. Right? So remember that the roof, the function, has to converge towards 0 for it to have a chance, but that's not good enough. It has to go fast enough. Right? And so the actual function is kind of hard to work with, so we introduce this other function, and then we establish that this larger function does converge towards 0, so the area underneath the blue converges. Well, then that must mean that the area underneath this red part must also converge since it's smaller. Good. Questions, questions, questions? Good. So by the comparison test, we established that that function converges. Good, 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 good. Okay, that's the end of the PowerPoint. Let's look at some problems from that section, and then we'll be all done from Chapter 7. Okay, 7.8. Let's kind of flip through some of the problems in the homework and maybe try a couple. Explain why each of the following integrals is improper. Okay, so let's look at number 1. What's wrong with it? How do we know that this is an improper integral? Because here's the problem: when x equals 1, x equals to 1, we're dividing by 0, right? We're going to have a vertical asymptote there, and we're trying to integrate from 1 to 2. That's going to cause a problem. If this had been the integral from 3 to 7, no problems, right? The function itself doesn't have a vertical asymptote there. Good, 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 good. What about this one? Well, easy to spot. It's got an infinity there, so that's an improper integral. Easy to spot. It's got a negative infinity, positive infinity. That's an improper integral. These are trickier, right? Spotting these is a little harder. Cotangent has, remember, this is cosine over sine, but sine of 0 is 0, so it's going to have an undefined. Cotangent of 0 is undefined. Good. So that's where the problems lie. Which of the following integrals are improper and why? Okay, so same thing. Let's try some of these guys down here. Number 5, number 6, 7. Let's try something in between 5 and, well, one of these guys maybe. Any suggestions? Any recommendations? How about 8? All right, why not? Let's try 8. So let's integrate. Let's find this integral here. Number 8. So this is chapter 7, section 8, number 8. So we have the integral from 1 to infinity of 1 over 2x plus 1 cubed dx. Good. So right away we can spot that this is an improper integral because it has that infinity symbol there. So we know we can change it. The limit as, what letter should I use? About E, Z, Q, T, how about K? The limit as k goes to infinity of the integral from 1 to k of 1 over 2x plus 1 cubed dx. Okay, so that's really the new part in chapter 8, this part, doing this step. And now this is just our old techniques for integrating anything. And this one's pretty easy, right? We can do kind of a little bit of a guess and check of what this would be. And so if we think of it as this, if we think of it as the limit as k goes to infinity of the integral from 1 to k, and we think of this as 2x plus 1 to the power of negative 3 dx, then I think it becomes pretty easy to see the answer. That the answer is going to be equal to the limit as k goes to infinity of 2x plus 1 to the negative 2 power. Right, so if we do it like this, we're going to get this term. We bring this out in front, and then we subtract 1, so we'll get that. But if we bring it out in front, we want to balance it out, so we already know we have to multiply by negative 1/2. So we're getting closer to the answer. Except then we have a chain rule that will produce yet another 2, right? Times the derivative of the inside part gives you another 2. So we also have to multiply by another 2. Good. And all of this gets evaluated from 1 through k. Let's put this over here now and simplify it. This is equal to the limit as k goes to infinity of negative 1/4. Well, let's go back to writing it in the other direction. 1/4 times 1 over 2x plus 1 squared, evaluated from 1 to k. Good. I'm going to move out that negative 1/4. Negative 1/4. The limit as k goes to infinity of, and then we have 1 over 2k plus 1 squared minus 1 over 2 times 1 plus 1 squared. Good. Well, k isn't going to affect this at all, so that's going to be equivalent to negative 1/4. The limit as k goes to infinity of 1 over 2k plus 1 squared minus, I should put that in there, minus, and this is going to be 2 plus 1 is 3, that's going to be 1/9. As k goes to infinity, this whole thing is going to go towards 0. So that takes care of the limit. And we're just left with this. Okay. So we'll end up with negative 1/4 times negative 1/9. So the whole thing is going to be equal to 1 over 36. Good. So it's equal to a finite value, therefore this whole thing converges. So the integral from 1 to infinity of 1 over 2x plus 1 cubed dx converges. Any questions? It's not too bad, right? You just have to break it up into a limit of an integral. Hopefully the integral is not too bad, and hopefully the limit is not too bad. But you could have a double whammy, where the integral is pretty tough, and then when you're finally done with an answer, you come back and try to implement the limit, and now the limit might be also pretty bad. So sometimes they're extra fun. Remember that we have tools at our disposal if we want to implement limits. Don't forget about L'Hopital's rule. So feel free to use it if you need it. All right, how about something in the tens? Any volunteers? Any questions on any of these? Has anybody had a chance to start the homework on any of these? Any suggestions? Any at all? How about 18? Seems like a nice one to try. Sure, let's try 18. Unless somebody else has a different suggestion for something in the tens.
No, that's fine. Just do number 18, Professor.
Number 18. All right, let's try 18. 18. Any ideas on how we'd want to start that one? Chapter 7, Section 8, number 18. And it's got the integral of from 2 to infinity of, oh, I hate b, b squared plus 2b minus 3 db. Okay, so first of all, let's try and factor this. So that'll be equal to the integral from 2 to infinity of two numbers multiplied in -3 but add to positive 2. It'll be positive 3 and minus 1. So that'll be b plus 3 b minus 1 over 1 dv. Right, so guessing and checking here, yep, that gives me that guy. And then we have problems here when v equals -3. Luckily, that's not a problem here since I'm integrating from 2 to infinity. But also we have another problem here at 1, right? Yes, so this function has vertical asymptotes at v equals to -3 and v equals to positive 1. So 1 over v squared plus 2v minus 3 has vertical asymptotes at x, oh not x, at v equal to -3 and at v equal to positive 1. Well, -3 is not a problem since I'm integrating from 2 to infinity. And 1 isn't a problem either. Can I copy this right?
Yeah, I think it's dv divided by v squared plus 2v minus 3, right? Is that the problem?
Yeah, I think so. V squared plus 2v. Let me. I think I have the right problem. Whoops. Yeah. 18. Yep. V squared plus 2v minus 3. Okay. So luckily, there's no problems there. I'm integrating from 2 to infinity, so there's no problem there. There's no problem there. If this question had been written this way, maybe it was trying to get us to integrate from negative 2 to positive infinity, we'd run into a problem because of the 1. There's a vertical asymptote there. But luckily, that's not a problem. Okay, so the only thing we have to worry about is the fact that there is an infinity symbol there. That's all. But we got to figure out what this is. All right, so from, I think, section 7.4, we learned that what we want to do here is find a way to rewrite that using, say, an addition or subtraction of simpler fractions so we can figure out what this is. So maybe kind of go off to the side here and do a little bit of side work. Oh, I guess I'll put it down here. We want to figure out what this is. V plus 3 times V minus 1. And that's going to be some constant, V plus 3, plus some constant, V minus 1. And there's 2 constants out here that we want to solve for. Good. Multiply both sides by that denominator. We end up with 1 equals to A, V minus 1 plus B, V plus 3, right? I got that by multiplying this side by, come on, this side by V plus 3 and V minus 1, and then the same thing on the other side, V plus 3, V minus 1. So all of this cancels, leaving me just a 1. And then when I distribute, I end up with this. Good. So now if I, again, distribute this, I get 1 equals to AV minus A plus BV plus 3B. Good. So the constants, I end up with 1 equals to A plus B times V minus, I'll just put plus 3B minus A. So I can add the extra variable of V. This is going to be 0 times V plus 1, which means that this part must be 0. I can conclude that A plus B must be 0. Therefore, B equals negative A. Or the other way around, A equals to negative B. Or, and then the other conclusion is that this must be that constant of 1. So 3B minus A minus A minus A must be 1. Good. But we also got that one of these two, it doesn't matter which one. So let's say that we replace the A. The A is negative B, so we get minus negative B. 3B must be 1. So that must mean that 4B equals to 1, and so B must be equal to 1/4. And since this was also true, it must be true that B equals to negative A. Oops. The other way around. A equals negative B. A equals negative B from there. So therefore, A is equal to negative 1/4. Okay, so we get that this guy is negative 1/4, and this guy is equal to positive 1/4. Good. Questions, 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 questions? Okay, so now that we've gone through all that trouble, we can come back to this guy, come back to the pack here, and say that this is going to be equal to the limit as, let's use, I don't know, how about, let's say u. Limit as u goes to infinity of 2 to u of this guy, which is equal to negative 1/4 over v plus 3 plus positive 1/4 over v minus 1 dv. Good. Okay, so that's going to be pretty easy. That's equivalent to the limit as u goes to infinity of these guys. And so the first one is just going to be equal to negative 1/4 ln absolute value of v plus 3 absolute value plus positive 1/4 ln of absolute value of v minus 1 absolute value evaluated as v ranges from 2 to u. Good. Okay, so we can factor out that 1/4. Let's put this over here and say that this is equal to positive 1/4 ln of limit as u goes to infinity of, and then I'm going to switch these around since this is a minus here. I'll put the ln of ln, come on, ln of v minus 1 minus ln of v plus 3 which is then equal to positive 1/4 the limit as u goes to infinity. Oops, forgot to put my limits of integration here. This is as v ranges from 2 to u. And this is then going to be equal to the limit as v minus 1 over v plus 3 absolute values evaluated from 2 to u. Good. All right, so then this is going to be positive 1/4 the limit as u goes to infinity of, okay, plugging in a u in there, we get ln of absolute value of u minus 1 over u plus 3 absolute value minus ln of absolute value of 2 minus 1 over 2 plus 3. This thing is so slow. Stop doing that. Okay. All right, now this guy in here, what are we going to do with this? Limit as this equals that. This is going to go, this is going to be the limit of, it'll become 0. I can put it over here. Yes. Is there a question? No. Well, okay, this is going to be limit as u goes to infinity. This thing, I guess I could break it up again, and maybe I shouldn't have brought it together. If we break it up, then we end up with infinity minus 1 and infinity less than infinity over this. Okay, this is going to be equal to the ln of, okay, we get to bring in, oh, okay, that's fine. This guy. Absolute value of u minus 1 over u plus 3, and then minus ln of 1/5 absolute value. So this is just some constant we don't have to worry about. So really this is the issue, figuring out what this is. And if you recall, when we work with limits, ln is a continuous function, so we're allowed to swap orders here, so we can stick this in here and figure out what this is. So this is going to be 1/4 times, and now instead of finding out the limit of both of these, I need to figure out ln of the limit as u goes to infinity of this part, u minus 1 over u plus 3, just figuring out what that is, minus ln of, and I don't need the absolute values anymore. Okay, as u goes to infinity, same thing. I'm looking at very large positive numbers. So for very large positive numbers, I'm going to have a positive number divided by a positive number. So I don't even need those absolute values either. Okay, so I'm just going to get rid of that, and maybe it looks a little simpler without having to deal with that absolute value. Right? That's because these are going to positive infinity. Okay, so the way it stands, I have an infinity over an infinity. Good. So remember that I'm allowed to find the derivative of the numerator, derivative of the denominator. I'll end up with a 1 over 1. So this whole thing ends up being, converges to 1. Right? By L'Hopital's rule. I'll write it down. This is equal to 1/4 ln of, and then by L'Hopital, let's L'Hopital it, I end up with the derivative of the numerator. This is going to be equal to the limit as u goes to infinity of the derivative with respect to u of the numerator divided by the derivative with respect to u of the denominator minus this ln of 1/5, right, after we L'Hopital it. So that's going to give us a 1 over 1. The whole thing converges to 1. So I just have ln of 1. 1/4 times this whole thing. And the 1/4 was, if it's not clear, the 1/4 is being multiplied by the whole thing. So it's this. And now I have ln of 0, I'm sorry, ln of 1, which is 0. I hate how messy everything ends up being on this. Ln of 1, right? I end up with a 1 over a 1 minus ln of 1/5. This guy becomes 0. So I get 1/4 minus ln of 1/5, or negative 1/5. One-fourth ln of 1/5, and there's a minus there from this guy. And then one more little trick, we can rewrite this as negative 1/4 ln of 5 to the negative 1 power. Now remember that one of the properties of logs is that you can move the exponent out in front like a linear factor. So this little minus 1 here, we can move out in front and end up with an extra little minus 1 ln of positive 5. And then there was this negative 1/4. The positive and the negative cancel. So my final answer would be 1. So therefore, the original function converges. So let's see if we can. Boy. So zoom out here. Wow, that was a big problem. Where are we? Oh, there. So we started out with this original question. We wanted to see if this converged or diverged, or figure out what that area is. So we separated this denominator as the product of these two binomials. We rewrote this integral, right? This improper integral that goes out to infinity. We rewrote it with some constant u, the limit as u goes to infinity of this integral from 2 to u. We were able to separate this fraction into the summation of these two fractions, each one a little easier to integrate, which we were easily able to integrate. And then it was just a matter of figuring out if that result, when we apply the limit, converged to a constant or if it diverged. So after a whole lot of work, we see that it equals 1/4 ln 5. Right, so I can just to kind of skip all of that and make it neat, I can say that this whole thing equals to 1/4 ln of 5. So that means that I have the actual answer, but I can also conclude that this original integral, this original integral from 1 over v squared plus 2v minus 3 dv converges. Okay, any questions? No. All right, let's see. Can we do something in the 20s? Can I interest you in something in the 20s? Anything interesting there? Let's get to one that has something like these. So we have a problem here because we're trying to integrate from 0 to 5. And then when we put a 5 minus 5 is 0. So the whole thing end up with a problem here, right? So maybe number 28 might be a good one to try. Or number 30. The problem with 30 is going to be that if we let x equal to -1, we have a problem. What do you guys think? 28, 30, 32? Let's try 30. Let's see, 30. This is chapter 7, section 8, number 30. Oh wait, did I say 30? Number 28. 8 has integral from 0 to 5 of 1 over the cube root of 5 minus x dx. Good. And so we notice that we have a problem right here when x equals to 5. When x equals 5, we end up with our function value f of 5 equals to 1 over cube root of 5 minus 5, which is equal to 1 over 0. Come on. 1 over 0, which is undefined. Right? We have a vertical asymptote there. So we're going to have to fix this by saying, all right, let's make it the limit. And how about A, B? How about B? The limit of B, and we want to integrate from 0 to, well, okay, the book likes to use A. Let's use A. The limit of A, as A approaches 5 from the left-hand side. And we want to integrate from 0 to A of 1 over the cube root of 5 minus x dx. Good. Well, that's kind of the hard part. The rest should be not too bad. So the limit as A approaches to 5 from the left-hand side, I'm going to rewrite this as 0 to A of, and writing it as this fraction, x minus 5, 5 minus x, 5 minus x to the power of negative 1/3 dx. That's the same thing as that, but I haven't done anything at all yet. And then writing it that way, we can see that the property of adding 1, right, the little pattern works. So this is equivalent to the limit as A goes to 5 from the left-hand side of come on. This is equivalent to 5 minus x to the power of positive 2/3. Right? If you think about reverse engineering this, so we bring the constant out in front, subtract 1, subtract 3 over 3, we get negative 1/3. Of course, we don't want that 2/3, so we got to multiply it by 3 over 2. Good. All of that gets evaluated from 0 to A. Good. Questions, 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 questions? And then the chain rule also tosses in an extra minus in here. Right? So you have to throw in that extra minus 1. Let's make that minus. Good. Questions, questions, questions? All right, so let me rewrite that over here. That'll be equal to the limit as A goes to 5 from the left-hand side of negative 3 over 2, 5 minus x to the 2 over 3 power, evaluated from 0 to A. So this would be equal to the limit as A approaches to 5 from the left-hand side. We don't need that constant, it's just getting in the way, so let's just pull it out in front and say there's a negative 3 over 2 out there. And then in here I end up with 5 minus A to the power of 2/3. Come on. 2/3 minus, and then it's a 5 minus 0 to the power of 2/3. 5 minus 0 is just going to be 5 to the power of 2/3. That's just some constant number. I just really need to figure out what this is. Good. So this is negative 3 over 2 times, and then in here this will be the limit as A approaches to 5 from the left-hand side of this function, 5 minus A to the power of 2/3, which is the same thing as, let's rewrite it this way, 2/3 power, that's the same thing as the cube root of, and then that whole function gets squared, so I'm going to write it like that. That's the same thing as saying that this is the cube root of, and then this whole thing is getting squared. Right? That's the power of 2/3 minus, and then that's the same thing here. I'm just going to rewrite it as 5 to the power of 2/3. Good. Same as before, we utilize this property that because this is a continuous function, then I get to submit this into here. And so this would be equal to -3/2 times, and this is going to be equal to the cube root of something squared, which is equal to the limit as a approaches to 5 from the left-hand side of 5 minus a. Good, good, good. Okay, so as a approaches to 5 from the left-hand side, it means it's going to be a number very, very close to 5, but always a little bit smaller than 5. Good? Always a little bit smaller than 5. But in this case, it doesn't really matter since you're cubing it. At any rate, this is approaching 0. Right? That's what this is going to say. It's approaching 0. And the cube root of 0 is going to approach 0. And something approaching 0 being squared, that whole thing is just going to approach 0. No matter how you slice it, this whole thing is approaching 0. Good. And so there's still this minus 5 to the power of 2/3. And so we end up with this times that. So our final answer is going to be positive, well, I'll just put them together, -2/3 times -5 2/3 power, and the negative cancel, so my final answer here is going to be positive 2/3 times 5 to the 2/3 power, which is again some constant. So we've established that this integral converges. Once again, we've got a convergent answer. Good. So that means that the original integral that we were asked about converges. So the integral from 0 to 5 of 1 over the cube root of 5 minus x dx converges. Not only do we know it converges, we actually know what it converges to, so we actually do have the exact answer for it. Questions? Questions?